All right, we toss around words like work, energy, and power every day, right? But what if I told you that in the world of physics, these words mean something completely different? And trust me, it's probably not what you're thinking. So let's dive in and figure out what's really going on.
So let's just start with the super simple question. Think about it for a second. What is work? I bet your mind immediately goes to something that takes a ton of effort, right? Something that just leaves you feeling exhausted? Well, here's the kicker. What if all that effort, in the eyes of a physicist, counts for absolutely nothing?
I mean, look at this list. Studying for a huge exam, pushing on a giant rock that just won't budge, or even just standing there holding a heavy load over your head. We would all, without a doubt, call this hard work. It's draining. You can feel the energy just leaving your body.
Okay, but here comes the big twist. From a purely physics standpoint, you could have done zero work. Yep, you heard that right. All that sweat, all that effort, that feeling of your muscles screaming, it could literally add up to a big fat zero. How is that even possible?
All right, let's unpack this whole no work workout thing, because it sounds kind of crazy. It all boils down to one simple fact. The scientific definition of work is super, super specific. It's way stricter and, in a way, simpler than how we use the word every day.
And this right here, this is the absolute key. See, in our daily lives, work is all about how much effort we put in, how tired we feel. But for a scientist, nope. It has nothing to do with your feelings and everything to do with one simple question. Did something move?
So for something to count as scientific work, you need two things, two conditions, that's it. Number one, you've got to apply a force, a push or a pull. And number two, and this is the crucial part, the object has to move. It has to be displaced. If there's no movement, it doesn't matter how hard you're pushing, no work is done, period. End of story.
And this brings us to a really simple little formula. Work equals force times displacement. So let's go back to that huge rock we were talking about. You're applying a massive force, right? But what's the displacement? It's zero. The rock isn't going anywhere. So force times zero is zero. The work you did on the rock is nothing.
So how do we actually measure all this work? Well, we use a unit called the joule. And to give you a feel for it, think about this. A newton is roughly the force it takes to lift a small apple. So if you push with that much force and you move something 1 meter, boom, you've just done 1 joule of work.
Now, here's something interesting. Work can actually be positive or negative. It all depends on the direction. So imagine you're pulling a little toy car. Your force and the car's movement are in the same direction. That's positive work. But what about friction? It's always pulling back against the motion, so friction is doing negative work, trying to slow that car down.
Okay, so work is all about a force making something move. But that begs the question, right? Where does the ability to even apply that force come from in the first place? Well, that leads us perfectly into our next big topic, energy.
Energy, when you strip it all down, is just the capacity to do work. That's it. If something has energy, it has the potential to push or pull on something else and make it move. And hey, notice the unit. It's the joule again, same as work. That's no accident. These two concepts are totally tied at the hip.
Now this capacity to do work, this energy, it comes in all sorts of flavors. But for what we're talking about today, let's just zero in on two of the big ones, the energy of motion and the energy of position.
First up, we've got kinetic energy. This is the energy an object has simply because it's moving. And when you look at the formula, you see something wild. Yeah, mass is in there, but velocity is way more important because it's squared. Think about what that means. If you double your speed, you don't just get double the energy, you get 4 times the energy. That's exactly why even a small object moving super fast can do a ton of damage.
All right, on the flip side, we have potential energy. This is basically stored energy just waiting for its moment to shine. Think about a stretched rubber band or water at the top of a waterfall. It has the potential to do work. See? A really common type is gravitational potential energy. The higher up you lift something, the more of this stored energy it has.
But here's the really cool part. These two types of energy aren't separate little boxes. They're constantly changing back and forth into each other. You have an object sitting way up high, that's all stored potential energy. But the second it starts to fall, that potential energy starts turning into kinetic energy, the energy of motion. Let's actually watch this transformation happen with some numbers. Look, at the very top, it's all potential energy, 800 joules, and 0 kinetic. But as it falls, just watch. The potential energy goes down and the kinetic energy goes up by the exact same amount. But here's the clincher, the most important column, the total. It stays locked at 800 joules the entire time. It's just shifting from one pocket to the other.
And what we just saw, well, that leads us to one of the most bedrock fundamental laws in all of physics, the law of conservation of energy. It's simple but profound. Energy can't be made out of thin air, and it can't just disappear. It can only change from one type to another. The total amount is always the same. So think back to you pushing that rock and getting tired. That energy didn't just vanish into nothing. It had to go somewhere.
So let's recap. We've got work, which is force making things move. We've got energy, which is the juice you need to do that work. But there's one more piece of this puzzle, and this one is all about time. And that, my friends, brings us to power.
You got it. It's not just about what you do. It's about how fast you do it. Imagine 2 people have to lift the exact same heavy box onto the exact same shelf. They both did the same amount of work, right? But if one of them does it in 20 seconds and the other takes a full minute, we'd all agree the first person is more powerful.
And that's exactly what power is in physics. It's the rate of doing work. It's how quickly you get the job done, or how fast you transfer energy. We're literally just asking, how many joules of work are you doing every single second? And we have a name for that unit, the watt. 1 watt is just 1 joule per second. Simple as that.
This example makes it crystal clear. We have 2 girls, both climbing an 8-meter rope. They're lifting the same weight, the same distance, so they do the exact same amount of work, 3,200 joules. But girl A zips up in 20 seconds, while girl B takes 50 seconds. Now, let's do the math. Work divided by time. Girl A's power is a solid 160 watts. Girl B, only 64 watts. See? Same work, totally different power.
Now, you've probably seen kilowatt written on your microwave or your air conditioner, and there's a good reason for that. When you think about the sheer amount of energy a house uses over a whole month, the joule is it's too tiny of a unit. It'd be like measuring the distance to the moon in inches. That's why your electricity bill uses a much bigger unit for energy, the kilowatt hour.
So what is a kilowatt hour? It's just the amount of energy a 1,000-watt device uses if you leave it on for a full hour. And that 1 unit is equal to a whopping 3.6 million joules. Yeah, it really puts into perspective just how much energy we're constantly using in our daily lives.
And this brings us full circle, right back to where we started, with you pushing that unmovable rock. You pushed, you strained, you burned through the chemical energy in your body from the food you ate, but you did 0 scientific work on the rock. So we have to end on this one last really fascinating question. If the energy you used up didn't go into moving the rock, then where in the world did it all go?